problem that I raised from the female bat in the forum, and unhonesty. So my colleague, not, okay, still my colleague.
Always your colleague. Okay, these are thermal baths in Pompeii. Of course, this will be a very, very brief presentation, quite a run. And so this building was discovered in 1832, and it's located near the Forum and behind the Temple of Jupiter, and date back of the years immediately following the establishment of the veterans of Generale Silla. Women and men and women sections of the bath are separated, have a separated entrance. And this build has been used for many, many years, probably since it's discovered as a depository for archaeological materials and also for human remains. So it was really occupied by savings, and so in the past we couldn't see the quality of the wall, and so it was really a discovery, as you can see here in the window, before and later, because for a very, very high layer of material, concretion materials, the decorated painting walls was very wasn't visible for now, and also something for the ceiling, for the internal part of the vault that was dark in origin, and now it was about brown, as you can see on the left. But we checked the differences, and so also with the laser techniques, we can result in discovering this fantastic decoration. And you can see the traditional part of walls with black basement part and white layer. And this is the final final phase of the restoration work, with a kind of harmonization of colors in the way to get similar old and also modern techniques. And it was a little balneum at the origin, and it's now during the restoration work. And later we discovered these fantastic frescoes with birds and plants, really, really beautiful. As you can see, this is in the past, and this is now really a discovery for us. At the entrance, where the woman were waiting for entrance to the bath, there are many graffiti. Here you can see on the right a kind of ship, and also a kind of bird or kitchen, also in the entrance with the seats. And this is at the end some graffiti not so apt for women. That's all. Thank you.
So, thank you. And yes, okay. Just to introduce the next speaker here. Is that one? No, vado io. No, era già aperto. Ok? Okay. So that's now we just to take the the argument. We talk about the monitoring, and actually, regarding the detail level, we know that we have a monitoring project also with the University of Salerno and with the other park in so Colosseo Park, Campi Flegrei, Paestum, and so on. And so we are planning now to improve our sensors around the city, and also to use a robotic total station. And in this topic is related what the next speaker that is Dora Foti, because also she's going to find a new solution for monitoring so the terme femminili, the female baths. Actually, we had a project for monitoring this because there is a very important fractures on the vault. But for this reason, we realized that it was important to first analyze the vulnerability of these structures, but not only of the complete structure, but also of the non-structural element. This small, thin wall that they are in the calendarium. And this is the project that we had with the Politecnico di Bari. And also, during these 2 years, we also present, Politecnico di Bari present an application to the digital library. So the Minister of Culture decided also to funding this project, and where they are using new structural monitoring, as well new technology, innovative detection, and using also artificial intelligence. This project is at the beginning, this new part of the project. It started 2 years ago with the vulnerability of the structures, but now we are going on, and so I invited Dora Foti, Professor Foti, to come here and present work that has been done up now.
Thank you very much, Alessandra. Thank you very much to all and for this invitation here. So, as Alessandra said, this project started 2 years ago, but now we got a financial support from Digital Library, and we started to buy some instrumentation that is more sophisticated to get more information regarding the structure and the non-structural elements of the terme, of the female bath building. Okay, so the women's baths were chosen as a case study due to the characteristics of their masonry structures and the decorative elements covering them. The need to preserve the integrity of this structure required the implementation of a geometric survey and monitoring program capable of detecting even minimal deformation of kinematic phenomena. Regarding the building, it has been exposed to environmental action for 2,000 years, more or less. And we have also limited structural data for ancient thermal systems, and for the high value, we need to get information on the health level of this structure by means of non-invasive methods. We have also to consider that the seismic zone is a seismic zone 2, that is almost the maximum high level of seismic zone in Italy. So how can we quantify the structural health without invasive intervention? So this is the problem, because of course we cannot touch the paintings, but at the same time the paintings are on the walls that need to be prevented from a collapse. Regarding the cases, this case study, it was built in the 1st century before Christ, and it was damaged in the 62 after Christ earthquake. And the main characteristic, that is the one that we need to preserve, are the radiant wall systems that are called tegule mammate for their shape inside their shape that is in contact with the structural walls of the building. So the structure is made of, it consists of Roman masonry plus plaster plus frescoes. And so this kind of walls need to be preserved especially for their stability, because they have value paintings on them. So the research objectives have been first a dynamic characterization of the Roman thermal bath, establishing a baseline structural properties and quantifying natural frequencies and most shapes. Then a multi-scale structural assessment, first for the global building, so to get the response of the global building, then the behavior and the behavior of the radiant wall panels, and then the dynamic behavior of the individual tegula. So 3 levels of assessment. Then another objective is to find out, to develop a non-invasive methodology that has to be applied in this case of important valuable heritage, with respect to the heritage constraint, that is not to touch the painting, for example, and not to use, of course, invasive methodology, enable future monitoring programs that we have to start, but we have not finished yet, and to find out a generalization of this approach. Finally, to validate the computational prediction by means of models, finite element model, that have been to calibrate in order to have a digital twin of the building and of the radiant walls, and also to get the load transfer mechanism, to get more information regarding how they behave, the tegula mammate behave, and which is the health state of this element, non-structural element. So, for the survey instrumentation that has been carried out by the group of designers of the department, is a tradition, consists of a total station, and a total station with a high precision, laser scanner to get information of the global building, and then a photogrammetry by a Canon R1 with a very high resolution images. We have performed 16 sessions. And it has been essential also to identify the texture and the ornamental structure reference points, PRSO, the procedure. Here there is a drawing of the laser scanner result that has been performed utilizing Faro Focus S70 equipment, and the objective is to get high density 3D acquisition of the complex geometry of the thermal baths. The result is to get a detailed point cloud, that is point cloud, and so to get the information regarding 3D, the 3D drawing of all the building. So we get this 3-dimensional model for further test, and the point cloud forms the fundamental metric framework of the baseline model onto which the photogrammetric and topographic data are grafted. So to get information, by means of the total station, we used two kinds of reflectors, let's say. The most traditional is the first one, the calibration by means of the monitoring network, with a metric accuracy that is guaranteed by the network created with the total station. And the targets, the markers, were positioned exclusively on the ground and on undecorated elements, like those that you can see in gray in the photo. No markers or devices were applied to walls, frescoes, or valuable elements, and all that data were georeferenced on this stable network by means of laser scanner and photogrammetry. The other method that has been utilized is without the use of physical markers. That is applying the PRSO protocol by means of getting ornamental structure reference points. So we use to get these points details of the frescoes as reference points, such as corners of frames, intersection lines, edges of gaps. And these stable points are measured at a distance by the total station with a millimeter precision. In total, for this monitoring campaign, we utilize 57 PRSO points that have been monitored. And 4 survey sessions were conducted with a total station over a period of 3 weeks. And this enabled a high-frequency differential analysis of the 57 selected points to be carried out in order to determine the short-term stability. Regarding the accuracy, we got, by means of this procedure, we got a minimal error between 2 and 5 millimeters for the different photogrammetry sessions, while the accuracy of typing a single PRSO with total station is estimated at plus minus 1 millimeter, so a very small accuracy, a very reduced error. The result is here compared regarding the laser scanner resolution and those obtained by the photogrammetry and with the PRSO procedure. And this picture is just to get some information regarding this part that is still under evaluation, under study to get from all the data that have been recorded, and we are still performing some results. Well, regarding instead the dynamic identification campaign, we utilized a series of accelerometers and then also some other instrumentation that, for example, an acoustic amplifiers that exerted a forced force on the wall. That is more than an impact force. It was a forced vibration without touching the walls and without touching the valuable heritage. So the survey have been done just a few days ago, I can say on the 6th of November, and we got 12 measurement locations where we put some this instrumentation, I mean regarding the piezoelectric accelerometers. So 8 of them have been put outside to get the global structural response. 4 instead on the radiant wall panels. They were very small piezoelectric accelerometers that they were put just on those parts that were not frescoed. And also 4 more accelerometers on the tegula mammalia, also in those places where it was possible to put this kind of accelerometer. Very small, like a finger, smaller than a finger, but with a high sensitivity to get some information. Also, before this kind of dynamic monitoring, we also did the thermographic analysis to get the parts that were more singular, more particular. For example, okay, in the first, on the left side, we got the difference of the temperature from outside, from the up of the wall and from the base of the wall. And instead, in the other two pictures, we can see in the squared, the part that are squared, that there are some anomalies regarding the thermographic analysis. Anyway, by means of the thermographic analysis, we got a model representative of the level of degradation of the radiant walls. And it has been possible to develop this kind of model. The internal heat flux has been obtained also utilizing data from literature. And from this analysis, we got the detachment gaps between the frescoes and the tegulae. They have been identified and validated by the thermographic survey. Here there is a picture of during the monitoring by means of accelerometers. You can see where they have been put the two kinds of accelerometers. Here there is the total station to get information from these accelerometers. And what we used, as I said before, were ambient vibration and also force vibration by means of an acoustic vibrometer. It has been possible to see the first frequency of the wall that has been identified at 101 Hertz for the radiant wall, and other testing modes have been observed at 98 Hertz and at 104 Hertz. All the accelerometers were placed on the radiant walls, identified translational modes in the main two horizontal directions. Okay, then we got the modeling, the finite element modeling both of the global building and of the tegula mammate and the radiant walls. And here there are some information regarding the finite element modeling, but I can say that we are still getting the results and elaborating the data that we got from these interventions. So the achievements that we have got by now is that we reached the non-invasive assessment of both frescoes and underlying structure of tegula mammate, a quantitative metrics for conservation planning with a single session capability and rapid assessment for large sites, and finally a non-invasive heritage protocol that can respect the heritage constraints with comprehensive assessment. For the future, what we are supposing to carry out is the calibration refinement, I mean also of other mechanical testing, a 3D thermal modeling, also considering the complex heat transfer, a multi-site validation, an integration that to combine with other non-destructive testing methods. Finally, the idea is to get a standardized protocols and a globally deployment of this kind of assessment. Okay, thank you very much.
Thank you. Okay, so we go on because it's pretty late. And so I introduce Federica Trotta from, whoa, sorry. Let's go directly with their presentation, otherwise, because she had we thought that it was important also to think to the restoration of this non-structural element, and that is made on tegole mammate. And with the meeting with the Istituto Italiano di Tecnologia, we thought to this possibility to use a robotic system to restore it, because it's very difficult to restore this wall, because it's very the wall is and the non-structural wall are very thin, very small space between, and it's very difficult to reach this area. And so this project that Federica Trotta from Politecnico di Milano, together with the Istituto Italiano di Tecnologia, is developing a new robotic system to restore it.
Thank you. So good evening, everyone. I'll present this project that Alessandra has just stated, that it's called the Plantoids in Pompeii, Conservation of Detached Frescoes of the Calidarium of Pompeii using self-growing robot intervention. This project comes from the collaboration of the Archaeological Park with Politecnico di Milano, in particular Professor Simone Cinquemani and myself, and the Italian Institute of Technology with Dr. Barbara Mazzolai and Dr. Arianna Travaglia. So these are the topics that I will present today. I will start by introducing the problem that the park presented to us. Then I'll move to introduce to you the main topic of our research, which is related to bio-inspired robotics, and in particular self-grooming robots. Then I'll show you the robot design that we have made, and I will conclude with the photogrammetric analysis that we have carried out in the real case. So let's start with the problem that was presented to us. So the frescoes of the Calidarium of the Terme Femminili are clearly detaching from the walls. So our solution is to develop this self-growing robot that should be able to navigate an unknown environment, because of course it has to go in the interstices between the walls and the frescoes. Then it should be able to move around a tight space, since the spaces ranges from 30 millimeters to 70 millimeters, and then it should be able to do a monitoring activity and possibly intervene in the future. So let's take a step back by introducing the topic of my research, which is bio-inspired robotics. What does it mean, bio-inspired? It means to learn from nature to make a simplified and enhanced mechanism that can solve a task. The main difference between the traditional robots, which are rigid machines, is that these kinds of robots are flexible, are adaptable, they can move and interact safely with the environments. There are a lot of pros, but of course also some challenges with these robots. They are flexible, they are lighter, they have a safe human interaction, and usually they are made with biodegradable materials. But on the other hand, it's difficult to model them from the material and also the control point of view. And for this reason, they usually have a lower precision than rigid robots. Here we have some example. We have the Poseidon that is made by Cecilia Laschi, that is inspired by the octopus. Then we have the Grobot, which is inspired by vines plants from the Italian Institute of Technology. And we have the elephant trunk made by Hughes. So, in the context of bio-inspired robotics, we are actually interested in the self-growing robots. These are robots that are capable to mimic this biological growth. They can mutate, their bodies can extend and reshape to adapt to their surroundings. So the key difference between the traditional robots is the fact that they achieve the movement through growth with respect to traditional robots that move through locomotion. We can say that there are two big families of self-growing robots. You can see in the first video the one that can extend because they are made of a material that is folded into itself, and by pressurizing this material it unfolds, and so the robot can grow. And on the other end, in the second video, you can see the kind of robots that we are developing, which are the ones that can elongate thanks to additive manufacturing processes. Of course, once again, there are some pros and some cons. These kinds of robots can morphologically adapt. They are continuous, they are flexible, and they have an autonomous environmental response. But on the other hand, it's difficult to control precisely the growth process, and a particular attention should be paid to maintaining the stability during the extension phase. Also, to integrate sensor in soft bodies is not an easy task usually. So, moving to our particular case, our biological inspiration are plants, in particular plant roots, because they have this apical growth, which means that they grow from their tip. That for us is interesting because to have a robotic head where everything is, we can say, compacted inside in terms of components and sensing, makes these kinds of robots able to explore and adapt with the environment while they grow. These plantoids, we can say, were designed at the beginning for underground exploration, but of course, in our case, we want to target the aerial movement and the structured environments. Once again, some pros, they can adapt to diverse conditions, and most of all, they are gentle and they have a motion that is non-destructive, which is perfect for the application in the Archaeological Park of Pompeii, and can be reconfigured by directly controlling the physical parameters. On the other hand, the growth movement is a slow process. They have a limited control precision, and most of all, the material could wear over time. So, now I want to present the actual design of our robot. This is the CAD model. So our goal was to create a self-growing system that was able to explore unstructured environments. Since, as I said before, the spaces in the interstices between the walls and the frescoes ranges from 30 millimeters to 70, we have chosen an external diameter for our robot that is 30 millimeters. So the first goal that we had in mind was the miniaturization, we can say, the compactness, and of course we wanted a robot that was able to bend, so to freely move in the space, and of course the real-time fabrication that is related to the self-growing robot itself. There were a lot of challenges during the design phase. The alignment and the compact integration were kind of difficult, and now that we are performing some tests on the head, of course structural balancing and thermal management could be an issue. But how does this robot work? Basically, as you can see here in the animation, all the parts move with respect to the orange and gray part on top, which are the fixed part of the robot. There is a filament, then in our case is a soft PLA, that goes from the base inside the robotic head. It's heated up in a ceramic element, and thanks to this rotatory movement, it is deposited around the external circumference, and layer by layer creates the body of the robot. I will not discuss too much about it, but here's just to show you the gear train that we have designed in order to basically be sure that no matter the sense of rotation of our motor, the filament is always fed inside the robotic head itself. So let's move to the first prototype that finally we got. Everything here is custom made except for the motor. For now, the materials are mostly stainless steel and brass. And as I was saying before, we use for the printing of the body a soft PLA, which has a temperature of melting that is around 140 degrees Celsius, so a little bit high, but it's fine. So, moving to the activity that we have carried out, we can say in parallel with the robotic design, is our goal was to take out some measurements that were important for us to make sure that our robot was able and was efficiently able to work inside the park. So we have started with the external fresco scans that were sent to us by the Pompeii Park. And in this case, we wanted just to know on average for how high and how long our robot was supposed to grow. So you can see here we have like 3.5 meters for general spaces. And then what we have done was to use an endoscopy to take out some recordings in the interstices between the walls and frescoes. And this was done because, as you can see, there are these cone-shaped elements that you know better than me, probably they were used to hang basically the frescoes to the walls, but in our case can act as obstacles for the movement of our robot. So we wanted to take, thanks to these recordings, you can see here an example of a recording that we have done with, you can say, a better example of these cones. We wanted to reconstruct through photogrammetry you can say at least the first part of the interstice between walls and frescoes, so that we can take out some measurements and make sure that the characteristics of our robot can match the requirement from the real case. So, for example, is the robot able to bend as much as needed to avoid these obstacles, and other kinds of information related to that. So, just to conclude, what we have done so far was to design and have a first prototype of our robotic head, and we went to Pompeii to do this survey with the photogrammetric approach. Now, what we are doing right now, but I couldn't show you some tests because the robot is currently under some adjustments, so I couldn't bring it here. We are doing some tests to perform, first of all, what are the general characteristics of the robot, and to make sure to, of course, solve the first challenges that we have encountered that are mostly related to the high temperatures. And then, thanks to this analysis that we have done, we want to verify the matching between our robot and the fresco's needs to being sure that it can be deployed efficiently in the real case. So that's it, actually, for me. Thank you for the attention. And if you have any questions, of course, I'm here, or there is my email.
Really, thank you, because these first saw the results. There was just an idea to restore this interface, and this idea now is a reality. That we have the robotic system that enter in this small interface, and I can add the material to restore it, a connected wall to the non-structural wall. So it is tegole mammate, and is an unstructural wall, and the wall that is on behind is a very narrow space, and work in this area with a restorator is completely impossible, and so just a robotic system can go there, and this idea is wonderful. I like it for the beginning, and so thank you. So now we go to the next and following the last section. So it's decorative elements. And first, Giuseppe Scarpati, my colleague, and so he's going to present something about the House of Tiaso. Unfortunately, then Professor Colace was unable to come, and for the bad weather today. So, but anyway, the problems of the decorative elements that we find in excavation, we already have. So then connect also to the next section.
Thank you, Alessandra. Just a short presentation about new excavation at Region 9, Insula 10. The excavation activity at Insula 10 of Region 9 in Pompeii began in September 2023. The main objective was to clear a large, previously unexplored area, about 3,200 square meters, which had remained buried after work carried out between the late 19th and the early 20th centuries. Okay, the principal result was the discovery of a large domus extending across more than 3/4 of the entire insula. It has been nicknamed the House of Tiasus, thanks to the discovery of a sumptuous banquet hall decorated with Dionysian scenes. Yet this room is only the latest in a complex that has yielded many other splendid frescoes. The plan of the property can only be hypothesized based on comparisons with other renowned architectural complexes in Pompeii. The area currently uncovered is occupied by a large T-shaped hall, room 24, opening onto a courtyard, flanked to the east by an alcove, a peristyle palestra, and bath facilities built at the end of the 1st century BC and decorated in the 3rd and 4th styles. This sector is connected through a doorway and a corridor to a more ancient part of the house, undoubtedly the principal one, whose chronology is not yet certain, but which features a remarkably sumptuous architectural structure. The architectural typology recalls the Samnite houses of Pompeii, but the area currently emerging is the result of a renovation dating to the 2nd half of the 1st century BC. It consists of a large peristyle with corner columns bearing great tough capitals still to be excavated, along whose northern side opens a sequence of rooms. The architectural focal point is a rare Equus Corinthius, the 3rd known in the city, originally connected to 2 small cubicula to the east, and 2 symmetrical ones to the west. Beyond the corridor lies an exedra and a deep Equus triclinaris. This is a reception quarter with banquet hall and more intimate rooms intended to host the closest visitors of the household, the friends of the Dominus and the Domina, to whom the private bathing suite was also offered. The house of individuals, the houses of individuals holding public office, an additional, more private area was reserved for cultivating social ties and relations of greater intimacy and friendship. The Black Hall, with its 2 vignettes, depicts events that sparked the Trojan War shows in the earlier of the 2, the first encounter between Paris and Helen, a fateful meeting that would ignite one of the most famous wars in all of literature. In the quarter adjacent to the hall, a small room called the Blue Room, after the color of its walls, had been interpreted as a sacrarium, a small sacred chapel where cult images were kept in wall niches, along with objects for family rituals. The walls are adorned with personification of the 4 seasons and allegories of agriculture and pastoral life. However, the most important discovery is certainly the Hall of the Tises, which, more than a century after the discovery of the mystery frieze in the villa of the same name outside Pompeii's walls, once again offers the world an exceptional context, both in meaning and in artistic quality. The walls behind the colonnades that articulated the actual space of the hall are decorated with a single large composition in 2nd Pompeian style, datable at around 40-30 BC. It is a megalography, that is a frieze with figures slightly smaller than life size. Comparisons in the Vesuvian area are extremely few. The mystery frieze in the Villa of the Mysteries, room H in the Villa of Fanius Sinistro at Bosco Reale, and room 13 in the Villa 6 at Terzinio. To this must be added the remains, unfortunately very fragmentary, of a large 2nd style wall painting in the house of the Iliac Shrine, and the even more fragmentary ones from the Villa of the Papyri at Herculaneum. Outside Campania, the only 2nd style megalography with a similar theme has been found in Roman villa in the area of Arles in France. This is the reconstruction of this Equus. Thank you very much.
Thank you. So You had a little bit of the most amazing fresco that I just discovered. Anyway, also this this decorative surface had a lot of problems. Also, they decay with time. So we need to study how to control this decay. And for this reason, now we invite you the next two speakers. First, Andrea Campostrini, that will introduce the work that is done with the Istituto Italiano di Tecnologia, because where we have some project for the decorative surface, how to find. First is find the microorganism on frescoes, and the second one will see how to find a new technology to detect cracks that are not visible. So please.
Thank you very much, Alessandra. So today I'm going to present you this project, which is not a RePAIR, but so we changed the logo, but it's called TimeCH, and it's a collaboration between 3 different centers of the Italian Institute of Technology. And I've titled Seeing the Invisible under Microorganism on Fresco under the Hyperspectral Eye. So first of all, just a brief introduction of why do we need to preserve ancient wall painting. We know that fresco undergoes several degradation phenomena. In particular, I focalized on biological colonization, which is one of the main problems when we're dealing with the preservation of work of art, in particular fresco as well. So mainly when we have to deal with biodeterioration, the main goal is to remove it. So that's what we want to do. And normally when we have to apply a biocide, there are 2 different ways, let's say traditionally, or we use a broad action biocide, which means a biocide which can kill every kind of microorganism. This kind of application could have some negative interference, let's say, with the pretorical layers, so with our substrate, so it could be problematic. The other way is to use specific biocide. To do so, we need to characterize which kind of microorganism we have on the surface, and normally we need to take some sample, which even though it's not invasive, it still needs to be analyzed in a biological lab. It means we have to pay for it, and there is work to be done. The idea of the TimeCH new protocol is that it's not invasive, and is to find a different way to clean with specific space-specific biocides, so biocide which would act exactly on the precise microorganisms without using any laboratory analysis. The case study for this work is Villa di Diomede, here at the Parco Archeologico di Pompei, who has 3 different, and we focus on 3 different rooms that we called red room 1, red room 2, and yellow room 1. Of course, they have precise name, but for us it was easier to understand what we were talking about. The idea is that we used 3 different steps to study the degradation, the substrate, and to see how we could act. First, the use of terahertz scan that my colleague Fulvio is going to talk you about, so I'm not going to go any further in detail about that. And the use of hyperspectral imaging. And then use a machine learning algorithm that could deal with the hyperspectral imaging data. So why hyperspectral imaging? Thanks to this kind of technology, we can get some, let's say, pictures, which are actually data cubes, which are made of different wavelengths, and every wavelength is unique for each kind of material. Depending on the kind of substrate, in this case fresco, we could see different kind of materials, so pigment, binders, and the substrate, and also microbiological colonization. The hyperspectral imaging has some limitation in the analysis because it's a technology which has been made mainly for remote sensing, which means geological radar, for example, or the mapping of vegetal acquisition through radar. On really big images, let's say, and so where the difference is not really detailed, and in our case instead is a really close up, let's say, so where we need to see the very few details difference on the fresco image. And these software that work with this kind of images, let's call them, needs to have some reference library that, of course, there are few of them for the remote sensing, but not for the detection of biocolonization. And the third problem is that this kind of information and analysis produce a really large amount of data, normally, plus we have to add that the kind of different biocolonizators is huge. Like the different kind of bacteria, fungi, yeast that could be present on the surface, it's really wide. For this reason, we needed to create some new library for biological materials, and or work with an unsupervised software, which means a software which does not have to look for a reference, but just see the difference from the image he's working with. Here I represented the in situ analysis we did here in Pompeii, first with the radar, terahertz radar, then the hyperspectral camera, and then me and my colleague working on the software not from here, of course, but from home or work. The idea of the software is that we would be able, once he took the picture, let's say, to show us where the different kind of microorganisms are present on the fresco. But to do so, we needed to first to see which kind of information we were analyzing through the hyperspectral imaging. So we did some microorganisms study to see, and we did some sampling, non-invasive sampling on the fresco, and now we are still trying to exactly see which kind of bacteria and yeast are growing on the frescoes. That we found a lot of them, thanks to our center here in Naples. Here in Naples, we are doing the DNA extraction sequencing, and at the same time, we are also taking the hyperspectral information for the specific microorganisms, so with that we would be able to spot them on the hyperspectral image, let's say. At the same time, we need also to see which kind of pigments were being used on the frescoes, and to do so we did some non-invasive analysis thanks to XRF. And the software that we use has been validated for the mixing of pigments. Here I've reported this example where we can see a fresco, let's say, which comes from the RePAIR project actually, where we were able to identify the different kind of pigments that they were used, even in mixture, giving us an important value for also for the RePAIR project, but also in our case, because we could be able to see the difference from the microorganisms even when mixed, because we know that when we find microorganisms on a substrate, most of the time they're mixed together. So the take-home message for this presentation is that the basis has been established for the development of new diagnostic tool to deal with biodeterioration. And with the new time-CH non-invasive protocol, you would be able to avoid physical sampling, so we would not need it to doing in situ analysis, and we would be able to map different species. So before concluding, I would like to thank all the people that are working with me on this project, and of course, all of you for your kind attention.
Thank you very much. And so we continue with the last presentation that still is in the detailed level of assessment that we have in Pompeii. We are increasing this aspect, and also again with the Istituto Italiano di Tecnologia. And here Fulvia Gennari will present the results using, probably terahertz and these new technologies, in this new frequency band in order to detect the fracture underneath the surface. Thank you.
Thank you very much. Thank you very much for the kind introduction. So let's start with a really brief introduction, just to say what is terrestrial radiation. So terrestrial radiation is something that stays in between infrared and microwave. That means that it's characterized by a wavelength that is between 30 micrometer and 3 millimeter. And it's totally non-ionizing, so it's safe. It can penetrate many materials. It can penetrate inside the wall about a few millimeters. But important things to keep in mind here is that these are the wavelengths that we want to keep in mind, because the level of defects of details that we can resolve will be in this range. So I think that we can skip this part. Let's say something really briefly about how the instrument is done, and then we will skip to the results, basically. Okay, so the thing that you can see there, the white thing, is a robotic arm that is holding the radar with the optics on top of the radar. So we are working on a confocal scan mode, so we are focalizing the radiation on a surface, and with the help of this radar, of the robotic arm, we are able to precisely move the imager with a micromillimeter precision. So we can scan the areas with that kind of precision. The wavelength that we are using is 300 gigahertz, so the frequency that we're using is 300 gigahertz, so the wavelength will be 1 millimeter. And we will work at a distance that can be up to 30 millimeter far from the wall, so it's perfectly safe. We don't have to touch the surface of anything. With this kind of instrument, we can also decide which focal plane we want to scan, and this is interesting because we can decide which kind of reflection we want to have. So we can decide if we want to have both reflection and scattering from the wall or only reflection. We can also put the focal plane inside the object to have a more in-depth analysis of what we are looking at. Of course, doing this is cutting out and is having a signal-to-noise ratio that is not that good, so we will not see that much. But if we detect something on the surface, we can go a bit inside to see. Of course, the instrument will always be not touching the surface, but we can see if it's propagating or not inside the wall. So basically, this is a study that we did in the laboratory to see, okay, can you, no? Okay, this is better. Okay. So this is a study that we did in a laboratory, and I'm putting this slide here just to show you how this is working on a really easy case scenario. So here we what we wanted to do here was to understand what we will see in Pompeii. So we started with a tile that can mimic really roughly a wall, because we have 1 centimeter of ceramic and a glazed surface on top. So we break it and then we reconstruct it, and we saw what we can see here. So here what you can see in the second image, basically the radar is giving us this kind of, okay, in the lower two image, the radar is giving us this kind of signal. What are those kind of signal? Basically is the radar, okay, this is the radar signal that is coming back to the radar, but what does they mean? What do they mean? So the image that we can see is formed by moving along the radar signal, and it's plotting the intensity of the signal in that point. But the signal in that point, the intensity of the signal in that point, it means the intensity of the signal from the depth that we are choosing, because even if we leave the focal plane on top of the surface, what the radar is doing is that is sending a signal and is waiting for the answer of this signal. So it depends on the time of flight of the arrival of the answer. It can reconstruct the timing of the signal that is coming back to the detector, and by knowing the refractive index of the wall, we can reconstruct how far from the surface was the signal that is coming toward us. So basically, by moving along this signal, we can go in depth of the object that we are studying. We also try to do some really easy crack detection algorithms. So basically by working on the image, we can reconstruct where the crack is going and what we can see or not. So this is always something that we did in the lab. So going to Pompeii. So the project, the initial goal of the project, I show you the part of the crack because I will show you some crack in Pompeii. But the initial goal of the project was to study microorganisms. So we also saw that crack were very easy and really easier to study instead of microorganisms. So I will show you even those kind of things. So this is something that was in one of the 3 rooms that Andrea told you about. And so you can see there that there are some defects in the picture, the visible picture. There are some defects that we can detect with the terrestrialization. So there is this upper part here that is dark blue, that of course is this kind of thing. So, and there are those blue things here that can are the 3 white spots. So what is this image telling us? From these 3 things, what are they, 2 things, the 2 zones, what are they telling us? They are telling us that we are really sensible to the different in height, but also, if you're looking at here, we have this white thing that is coming, that has no real, at least it's not a difference in height in the visible picture. So maybe it's possible, we don't know yet, because we still have to put together the 2 results. So it can be that it's some maybe microorganism that is coming from that. So of course we study this kind of defects. We take the analysis further. So here we just apply PCA, and with PCA you can see that here there is still, and with K-means you can see that here there is this kind of yellowish thing that we had here in this previous picture. But if I'm moving, okay. No, sorry, I was moving the mouse, but I didn't realize that it wasn't showing there. So the red thing is the same thing that we were seeing in the previous picture. So we know that that thing can be another, can be a different thing, so something that is worth studying. Okay, perfect, thank you very much. Okay, so going forward, this is another part of the wall. So it's still in another room. So this is the still the visible image, and this is the terrace image. So if you in this case, if you study the surface of the wall, from the wall surface, you can just see this kind of crack here that it's visible from here. But then if you move along the signal, you can see that something here is appearing, this almost C-shaped thing. So we believe that this C-shaped thing is a crack that is under the surface, that is not actually visible from the surface of the wall. The same, wasn't supposed to be a translation here. The same thing we can do with, we did with other kind of, so I'm presenting you another analysis that we can have here. So this is still another crack, yet another crack. And here you can see that. So a visible image, the terrace image, and this is a point cloud analysis of the signal. So that is showing the different height, representing as a point different height of the feature that we can see in the picture. And from here is not really visible in this, sorry for that, but it wasn't really, the level of detail is that tiny that wasn't really showing that it was not really easy from this picture. But you can see that the crack is going down from the plane. So we have an understanding of how much was it deep. And with the same thing, I want to show you that basically, okay, the crack is visible, but also some other defects are visible. So this can be this thing here is something that has a difference in height, but if we're talking about this thing here, from the visible picture, there weren't any really any defects that were on top of the surface or not. So still, there wasn't any difference in height there. So we believe that here too we are detecting some microorganism, but yeah, we have to intersect the two results to tell you that. So thank you for the attention. Yeah.
Thank you very much. I was very fast, but well, we are a little bit late. But it was very interesting because we went really from the large scale to the small scale and to the invisible cracks. So it's so how we can monitor in well, really from the urban scale until really teeny small things. So thank you to everybody that was here until the end, and also the one that attended all the day. Thank you very much.